Hello, welcome back. In this video, we're going to learn about stoichiometry. So stoichiometry is a section of chemistry that's concerned with using the relationship between reactants and products to calculate how much of each is involved in a chemical reaction. So basically what happens is you'll be given some amount of reactants and products or reactants and told to find the amount of products that will be produced. All right, so let's go ahead and look at how we use stoichiometry in everyday life. So let's say we're given the recipe for making 12 servings of brownies, and we're told that the ingredients that we need are 2 sticks of butter, 2 cups of sugar, 4 eggs, a cup of flour, and 2/3 cup of cocoa powder to make 12 servings of brownies. We're told that we only have 6 eggs, but we have enough of all the other ingredients, and we want to know how many brownies can we make. So let's see how we would go about doing this. First thing I'm going to do is I'm going to write the recipe with the ingredients as like a chemical formula. So notice that all the ingredients represent my reactants, and the 12 brownies that I'm trying to make represent the products. So to figure out how many brownies 6 eggs give us, I start off with what I'm given, which is the 6 eggs. Right, so I write 6 eggs here. And I'm going to use my equation as a conversion factor. So I can see from my equation that for every 4 eggs, I can make 12 brownies. So notice that I came up with a conversion factor from this recipe, from the balanced equation. So for every 12 pieces of brownies, I need 12 eggs, or 4 eggs, sorry. So when I multiply this through, notice that the eggs cancel, and that leaves me with brownies. Okay, so this gives me 18 brownies. So I have enough eggs to make 18 servings of brownies. So notice that in this problem, I used the recipes as a conversion factor, and I used the brownies as the amount of product that I was given to figure out how many brownies I can make if I have 6 eggs only. So balanced equations are just like recipes for how reactants and products combine. So now let's look at an example of a chemical reaction. So I'm given, as an example, this chemical reaction here, and I'm told that if I have 3 moles of N2, and assuming there's enough of H2, how much in moles of NH3 can I make? So what I'm going to do here is, again, start off with what I'm given. I'm given 3 moles of N2, so I put 3 moles of N2 here. And I'm trying to figure out how much NH3 I can make, how many moles of NH3 I can make. So from the balanced equation, I can see that for every 1 mole of N2, I can make 2 moles of NH3. So I use that as a conversion factor. For every 1 mole of N2 that reacts, 2 moles of NH3 is produced. So this is now going to be used as a conversion factor. Notice that the moles of N2 here will cancel, and my final answer comes out to 6 moles of NH3. So I can produce 6 moles of NH3 if I have 3 moles of N2 and more than enough of H2. So in this case, I use the chemical equation as my conversion factor, and I use the coefficients, which are the numbers in front of each of the chemicals, to convert between one chemical and the other chemical. Now, in the problem that we just looked at, we saw that we can do a mole-to-mole conversion using the balanced chemical equation. Now, let's say I wanted to do a mass-to-mass conversion rather than a mole-to-mole conversion. Remember that chemical equations give us a conversion factor between moles of reactants and moles of product. So to go from grams of the reactant to grams of this product, what I have to do is first convert into moles, right? I would first have to convert the grams of A into moles of A. The reason I have to do that is so that I can use this balanced chemical equation as a conversion factor. And then after I convert into the moles of product, then I can convert into mass of product using the molar mass. So here is the roadmap. This roadmap is very similar to the one we saw in when we were looking at mole-to-mole conversion using the chemical formula. Now we're going to look at it as going from reactants to products. The way that we cross over from reactants to products is this bridge over here, which gives us a mole-to-mole conversion. This here is where we use the balanced chemical equation and these numbers, the coefficients that are in front of each of these chemicals. So if I'm given mass of a reactant, I first have to convert it into moles before I can cross over the bridge using a mole-to-mole conversion. And then I can, once I'm on the product side, I can go to either number of atoms of it or molecules of it, or I can go to grams of it using the molar mass. But in order for me to cross over this bridge, wherever I am on this map, I have to end up at moles. So keep that in mind. It's just like how we learned before, but this time we're going from reactants to products. But again, to go from reactants to products, it has to be a mole-to-mole conversion. All right, so now we're going to look at an example. So when B2H6 is burned in air, the following reaction takes place. If 5.46 grams of B2H6 is burned, how many grams of water are produced? Notice that in this example, they do not mention anything about how much oxygen is present. And that's just because this reaction is taking place in air. So when it occurs in air, we assume that there's unlimited amount of oxygen present. So how much product gets produced depends on how much B2H6 we have. So what we're going to do is look at the map that we have, the road map. What we're given is the grams of reactants, B2H6. So we're going to be starting off down here, and we're asked to find the grams of product, H2O. So we're going to end up over here on the product side. So that means I have to convert grams of B2H6 to moles of B2H6, and then I use the balanced equation to do a mole-to-mole conversion to moles of water, and then I go from moles of water to grams of water. Okay, so we'll go ahead and write this roadmap. Okay, we're going to start off with the grams of our B2H6. We're going to convert it to moles of B2H6, and then we're going to do a mole-to-mole conversion using the balanced equation to convert to moles of water. And then we're going to go from moles of water to grams of water because that's what they're telling us to find. So I start off with what I'm given, which is the 5.46 grams of the B2H6. Okay, and then what I'm going to do is I'm going to use the molar mass of B2H6 to convert into moles. So grams goes on bottom. Remember, it's always per 1 mole of B2H6. To find the molar mass of B2H6, I use the periodic table. So on my periodic table, B has a mass of 10.81. There are 2 of them, so I multiply by 2 plus there are 6 hydrogens, each one with a mass of 1.01. So when I add these together, I get that the molar mass of B2H6 is 27.68 grams. So this here will cancel the grams of B2H6. Now I'm going to convert moles of B2H6, right? So now we are over here, and now we need to cross over this bridge to here. So I'm going to use the balance equation. Moles of B2H6 goes on bottom. We're trying to get moles of H2O, so moles of H2O goes on top. To do this conversion, I use this balanced equation up here. Notice that according to this balanced equation, for every one B2H6, 2 water molecules are produced. So each 1 mole of B2H6, right, there's no number, no coefficient, which indicates that it's a 1, makes 2 moles of water. So that's what I'm going to put, 2 waters for every 1 B2H6. So now the moles of B2H6 cancel each other. I have one more step now where I convert some here. I need to convert to grams of water. And to do that, I use the molar mass of H2O. Moles of H2O goes on bottom. Grams of H2O goes on top. 2 times hydrogen plus oxygen is 2 times 1.01 plus 16 is 18.02 grams per 1 mole. And you can see now that these moles cancel and I'm left with grams of water. So I plug this into the equation, so 5.46 or into my calculator divided by 27.68 times 2 times the 18.02, and my answer should have 3 significant figures because 5.46 has 3 sig figs. So this gives me 7.11 grams of water. And that's my final answer. That's how much water is produced in this reaction. All right, so now we're going to look back again at the recipe we looked at before with the 12 brownies. This time, though, we're going to assume that rather than just having eggs as a limiting ingredient, we also have our cups of flour and cups of sugar as a limiting ingredient. So we have the same recipe as we did before, but now we have 6 eggs, 2 cups of sugar, 2 cups of flour, but more than enough of all the other ingredients. Now we want to know how many servings of brownies we can make. So this time what we need to do is figure out how many brownies will we get from 6 eggs, how many brownies will we get from 2 cups of sugar, and how many brownies can we get from 2 cups of flour before determining how many brownies we can actually make. So from the 6 eggs, right, remember we used the balanced equation. In this case, we made that from our recipes as a conversion factor. So 12 brownies for every 4 eggs, that gives us 18 brownies. So we have enough eggs to make 18 brownies. Now let's look at our cups of sugar. We have 2 cups of sugar. For every 12 brownies, we need 2 cups of sugar, so we have just enough sugar to make 12 brownies. And now let's look at the cup of flour. We have 2 cups of flour. Each 1 cup of flour gives us 12 brownies, so that means we can make 24 brownies for the amount of flour that we have. So what we notice is that we have enough eggs to make 18 brownies, enough flour to make 24 brownies, but we have enough sugar to only make 12 brownies. So we cannot make any more than 12 brownies because if we try to make 18 brownies, we run out of sugar. We don't have enough sugar to make that. So the most brownies we can actually make is just 12. Once we make our 12 brownies, we will run out of sugar. We'll still have some eggs left over and some flour left over, but we will be all out of sugar. So if this was a chemical reaction, we would say that 12 brownies are our theoretical yield. In theory, right, we can make 12 brownies. Notice that I haven't actually cooked my brownies yet. All I've done is calculated how much ingredients I have enough of for how much brownies. So 12 brownies would be called our theoretical yield or maximum yield, meaning the maximum number of brownies we can possibly make is 12, right? Because we might drop some brownies on the floor, we might burn some brownies, but if everything goes perfectly well, we will make 12 brownies. No more than 12, just 12. And if this was a chemical reaction, the 2 cups of sugar would be called our limiting reactant. Our limiting reactant determines the maximum amount of product that we can actually make. So we looked at this reaction where we make 12 brownies, right? Now, let's assume that we accidentally drop 3 of our brownies on the floor after we make it. So let's say we actually do this. We make our brownies, we cook them, and after we cook them, we drop 3 of our brownies on the floor. So we have now only 9 brownies left. The 9 brownies represent our actual yield or our experimental yield. The actual or the experimental yield are the numbers you actually get after you cook your whatever you were cooking or you were baking or you were making in the laboratory. Okay, up until that point, everything else was just calculations. Before we actually carry out the recipe, we wanted to know how many brownies can we make. That was our theoretical yield, right? So these numbers over here, this 12 over here for the 12 brownies that we said we have enough sugar for making just 12 brownies, this was all calculations. We haven't yet cooked our brownies yet. We calculated here that we can make 12 brownies. But then when we went and actually cooked our brownies, we made 12, but we ended up dropping 3 on the floor. So we only ended up with 9 brownies. So our actual yield is 9 brownies, also called the experimental yield. If we wanted to know how efficient our experiment was, okay, or what our actual yield or percent yield was based on our actual yield, the percent yield is equal to the actual yield over the theoretical yield times 100. Our actual yield was 9 brownies, so it's 9 divided by the theoretical, which was 12, times 100. Remember that the 100 has infinite significant figures. So our reaction, our percent yield was 75%. Okay. Now what we're going to do is we're going to actually look at an actual chemical reaction that involves 2 different ingredients, one of which will end up being limiting, and we have to determine which one. So let's say we have this reaction here, and in an experiment, 6.23 grams of the NH3 reacts with 4.78 grams of oxygen. And we want to know the maximum mass, right? The mass is in grams of water that can be produced. So in this case, we need 2 roadmaps. We need to go from the grams of NH3, right, which is our reactant. We're going to convert it to moles of NH3. Remember, we always have to convert the grams into moles because we need moles in order to do a mole-to-mole conversion to the moles of product, right? Because this balanced equation here gives me a mole-to-mole relationship between reactants and products. It's asking us for mass of water, so I would find the grams of H2O. I would do the same thing for the other reactant, which is oxygen. So I also need to go from the grams of oxygen, convert it to moles of oxygen, so that I can use the balanced equation to convert to moles of water and then convert to grams of water. Okay, so we start off with what we're given. For NH3, we have 6.23 grams of it. I need to first convert that into moles using the molar mass. Each 1 mole of NH3 has a mass of 17.04. Where do I get that? From the periodic table. Nitrogen is 14.01 plus 3 times 1.01 for the 3 hydrogens. Okay, so this cancels the grams of NH3. Then I need to go from moles of NH3 to moles of water. I would use the balanced equation, right? I would use these numbers here. Moles of NH3 goes on bottom. Moles of water goes on top. From the balanced equation, we can see that every 6 moles of water gives us 4 moles of NH3, right? 4 up here and 6 here. And then I convert this into grams using the molar mass of water. Each 1 mole of water has a mass of 18.02 grams. And then I just multiply this through. So it would be the 6.23 over the 17.04 times the 6 divided by the 4 times 18.02. And the calculator gives me to 3 significant figures because 6.23 has 3 sig figs. I get 9.88 grams. Of course, I'm not done. I have to do the same thing now for the grams of oxygen. For the oxygen, I'm told that I have 4.78 grams of it. So I convert that to moles, grams on bottom, moles of O2 on top. Each oxygen from the table is 16.00 grams. There's 2 of them. That makes 30.2.00 grams, right? The grams here cancel. Then I use the balanced equation from the table to go from oxygen to water. There are 5 moles of O2, right? So moles of O2 on bottom because I'm trying to cancel it. There are 5 moles of O2 for every 6 moles of H2O. So now the moles of oxygen here cancel. And then the last step is to convert the moles of water to grams of water because they're asking us for mass of water. Each 1 mole of water is 18.02 grams. Right, so the last step is the same for both reactants. So I start off with a 4.78. I divide by the 32.00 times 6 divided by 5 times the 18.02. And the calculator gives me 3.23. Again, 3 significant figures because of the 4.78. So now I have both of these two numbers, right? I have the 9.88 and the 3.23. The maximum that can be formed is the 3.23 grams. The smaller number is the amount that we can make, right? We cannot make 9.88 grams of water because we don't have enough oxygen for that. We only have enough oxygen to make 3.23 grams. After that, we run out of oxygen and we cannot make any more H2O. So the maximum that can be formed is 3.23 grams. It's asking us what the limiting reactant is. The limiting reactant is the reactant that determines the amount of product we make. So it's the one that we have the least of, in this case the O2, because it resulted in the least amount of the product. So our limiting reactant is oxygen. And then the last step asks, if the percent yield is 92.6%, what will be the actual yield of water? Remember that the actual yield is always less than the theoretical yield, right? So this here, this maximum mass that they had us find, this is our theoretical yield. Theoretical and maximum are the same. So now I need to find the percent yield. The percent yield is the actual yield over the theoretical yield times 100. I'm given the percent yield as 92.6%. that's equal to 0.926, which is equal to our actual divided by 3.23, because our theoretical yield is 3.23. And again, remember, our answer has to come out smaller than the 3.23 because the actual is always less than the theoretical. So the answer that I get is 2.99 grams. So that's how much product is actually produced. Okay, so these would be our answers. All right, so here are a set of practice problems for you to do on your own. So you can pause this video, do these on your own, and then look on the next slide for the answers. And here are the answers to the previous slide problems.